So we're going to wrap up our conversation of partitions by talking about a different type, which is a set partition. So instead of being an integer partition, I'm concerned with a set S. For example, I could take the set of numbers 1 to 5. And what I want to do is partition it into blocks. Here are my boxes. So once again, we're back to balls and boxes. And I want the boxes to have a certain condition. So first of all the numbers go into boxes. Okay, that's what the first one says. Every number has to get into a box. Every number goes into exactly one box. So I can't put the number 1 in both boxes. I have to pick. And no box can be empty by the time that I'm done. So I can think about the ways to do this if, for example, I've got these 5 numbers, right? And I've got these 2 boxes. How many different ways are there for me to do that? And the answer in this particular case is quite a lot. So let's think smaller. Let's think if I just had the numbers 1, 2, and 3. Now, how many ways can I put these into 2 boxes? Well, I need to put something here. So maybe I'll just put 1 and 2 here, and then I'll put 3 by itself. That's one way that I could have done it. Or I could have put 1 and 3 together and 2 by itself. And of course, that's the same as this. I don't care what the order of the boxes are. The boxes aren't specified in any way. So it's just about who goes with whom. And there, I could do it this way. I can't put them all together, and that's actually it. I've actually exhausted my list of possibilities there, and it looked like to me like there were 3. So let's do that as an example. And let's actually give it, sorry, let me back up and give it a name first. It does have a name, so let's talk about that. So the name that we're going to call these numbers that we're about to enumerate are Stirling numbers of the second kind. So S, that's a capital S, in K, which are the Stirling numbers of the second kind. No, you didn't miss the first kind. We haven't done them yet. This is the number of set partitions of 1 up to n into K blocks. So again, those blocks are non-empty. So we saw in this case that we get a nice answer. And in fact, we can think about, okay, well, what if we had 4 numbers? So let's do this. Let's try to figure out what is S4, 3. What is S4, 3? How can we do this? And let's think systematically, okay? So, well, no box is going to be empty, right? So how many different ways can I distribute my numbers into these boxes? Well, each box gets at least 1, right? By the pigeonhole principle, if you'll think back that far, because I have 4 balls to put into 3 boxes, at least 1 box gets at least 2 balls. But since each box gets at least 1 ball, I know that there's going to be exactly 1 box that gets 2 balls. Okay? So all I have to think about is which box gets 2 balls. So it kind of doesn't matter which box gets 2 balls. It just matters that that's what it's going to be. So maybe let's write that down. That S of 4, 3 is equal to, all I do is choose which 2, so it's 4 choose 2, which is 6, our favorite number. So that's kind of interesting, but did it matter that it was 4? So what if I decide to have 4 boxes and the numbers 1 up to 5? Let's run through the same argument again. So I'm going to fill these boxes. I have more balls than I have boxes, so at least 1 box gets at least 2 numbers, okay? But each box gets at least 1 number. So if I just think about that, I had 4 numbers get taken up. There's only 1 extra number to play with. It's got to go somewhere. So again, there's going to be 1 box that has 2 balls, and all the rest of the boxes have just 1. So it's actually the case that S of 5, 4 is equal to 5, choose 2. So there would be 10 ways to do that. And in fact, what we've just discovered is that S of n minus 1 is actually super nice. It's n choose 2. That's kind of neat. So are there other things that we could do? So that's when we have a lot of boxes. Well, if we only had 1 box, that was pretty easy. If we just have 1 box, everybody goes in the box, and there's only 1 way to do it. That's trivial, but let's write it down anyway. So we've discovered that if we take S, we want to put N and we have one box, there is one way to do it. Stick everybody in the box. Okay, let's do another case. Let's think about S of N2. That's another thing we could do. How would we do it here? So think about what we're going to have to do. We've got all of these balls, and we have to decide how to put them into boxes. So one is going to go into some box. So I might as well put it here, and now I can kind of think of this box as fixed. Because again, doing this doesn't change the outcome. I don't care about which box they go in. But now this box I can think of as the box with 1. And now I've got these 4 numbers left. And all I have to do is pick how many go in here, and then the rest will go in here. And I could take all of them. That's no problem. I could put all of these numbers into this box. Or I could put just some of them. I can't put none of them. Okay? So I could put the one here, and then I could put all of them in here, but I can't put none of them in here. So I just have to choose a non-empty subset of these numbers. And that's actually a nice theorem. So it's the number of non-empty subsets of the numbers, say, 2 up to n. So there are n minus 1 of these numbers. Well, the number of subsets is 2 to the n minus 1. And I said, just don't pick the empty set. And so there's a nice formula as well. So it turns out for a lot of the Stirling numbers, if you take this parameter to be really big or really small, you can get a nice concrete formula just by thinking in terms of combinations. Maybe anchor one of the boxes, or think about it like we did here in terms of, well, you have to have most of the boxes mostly full. So for your homework, to get you started, suppose you've got the numbers 1 to 5 and you want to fill up 3 boxes. How many ways can you do this? Well, again, let's just sort of think abstractly, but keeping it concrete at the same time. We've got these 5 numbers. So what does the pigeonhole principle tell us? It says more balls than boxes. So at least one box gets at least 2 balls. Now keep in mind that 3 numbers are going to get sort of anchored in there. So I know that 3 are already accounted for. So what could happen? What could the structure of my boxes look like? So if I'm doing S in n minus 2, that's this case, I'm going to have 2 options. So either I have something that looks like sort of a 3, 1, 1, where I end up with 3 of the numbers go here, and then I get 1 number there and there. Then all that matters is which 3 I chose. So that's an n choose 3. But then what else could I have done? Well, I could have had the structure of my boxes were 2, 2, 1, right? So I get 2 balls here, 2 balls there, and then 1 there. So now, how am I going to choose that? That's going to be for you to figure out and finish your homework.